modeling challenges that I came across the other day while thinking about um, disentanglement. Disentanglement in the sense of like, because I eventually want to get that model in a way that I can actually manipulate it as well, right? So you have the rules and you do the rule replacement stuff, and so with these you evolve the model, but then also you have to consider what happens when you disentangle things. And so hopefully the way this rule replacement happens should be in a way consistent with um, should be in a way consistent with. Give me a second to plug this. I keep trying whether my pen works and it never works, and then I always end up using the fucking mouse. Um, yeah, because for some reason it just gets in the wrong screen. Oh, there it is, actually. Yeah, but it's just it. This is awful. This is definitely awful. I don't know. We'll see. We can give it a try. So, and actually the problem I had was originated when I was thinking about the TOEFL gate. So remember there's this kind of um, hypergraph or the state sort of you can represent a specific state, which is I think the state where you have 0, 0, and 0, and then 1, 1, and 1. And then you have sort of like around these and around these, right? So this was to kind of represent the the state in which, so the initial state here, the initial state that leads to these is the plus 0, and then applying a CC not gate, that's kind of what you end up doing, right? So that those the double nested rules where you were kind of saying, okay, so you first split the 0 and the 1, and then you split another 0 and the 1, but then these two kind of get connected. So essentially what this hypergraph is telling you is if I know that this is a 1, then I know that these must be true. This is a bit of a special case, right? Because it's a bit of a special case because um, we have here nested is a hyperedge. So it's kind of, I think it's the only case I've come across, and I think that probably happens more with 3 qubits plus. Is the only case that where I've come across a situation where the hypergraph, so the hyperedge is actually nested, and that's what that actually matters, right? Because this means that it's the combination, it's the full hyperedge that's true, not necessarily these two nodes, which belong also to these one, right? So like everything within a hyperedge has to be true. This means all must be 1. Yeah. But that still, that still allows to, that model still answers questions correctly, as in like, if this is a 0, then I know that it's not a 1, and therefore these two, then I know so then I know that these two are not, what I know is true is that I know that these two are not 1, 1. I know that the hyperedge cannot exist. Like this cannot be true, because I know that this is not a 1. And therefore all the other 0, 0, 0, 1, 1, 0 combinations become valid answers. Now the problem is what happens when I do pos selection, because I've been working on the pos selection stuff, and so one way that I'm trying to approach this is to say, let's say I want to pos select on 0. Here is easy because the only 2 nodes that I have for the target qubit. So this is the target qubit. So the only nodes I have are actually orthogonal to each other. So I don't have any kind of like plus state where I also technically have to keep it for in case of pos selection. So I know that I'm only keeping these, right? So I know. Yeah, so I'm in the middle of kind of coding the algorithm, and one of the things that I thought was, okay, so I know that I'm keeping these, so how can I leave the hypergraph? So what will be the equivalent hypergraph after a pos selection and 1? So if I would pos select target in 1, then I would expect that the hypergraph, kind of you get rid of the zeros, right? Because I know that if it's a 1, this must be true. So I know that So I know that there's a zero here that they only uh, yeah, so there's a zero here that is not going to be realized, or we know that's not a valid node anymore. And so then we have all the other zeros that are nodes that belong to the same hyperedge, because remember that in reality, the whole system is also wrapped around one thing, right? So I'm not drawing it here for simplicity. And so the logic would be, I have other nodes that belong to the same hyperedge that I'm deleting these from, because I know that I'm invalidating the hyperedge by deleting this one, because I know that this can't be true. And so by definition, uh, yeah, and so that's kind of by definition, right, of yeah. I so I'm not sure if that doesn't, in essence break some of my definitions, but so I would say, yeah, I can't just delete things, right? It's not that if I know that if it's zero, these two are zero, because that's also not true in this model. I know that if this is zero, I know this is not the case, right? The other way, I know if it's one, this is not the case, right? So I can delete that. Now I can ask myself, well, if this is one, um, is this the case? Like, should I keep this node or should I delete this node? Now, do they share hyperedge? They don't, but that's still, they share one, which is the system hyperedge, right? But they still could be, if I ignore these, like there's nothing that tells me this can't be a valid answer. Um, because let's say that I do a post selection on zero, right? Like this qubit can still be one. Just because they don't share all the hyperedges doesn't mean that I can delete this node. So actually I think that is the wrong thing to do algorithmically speaking. Maybe that's the issue, right? So I don't know how to answer the question of, let's say I do a post selection. I feel almost like this was just a specific, what I had in mind was a specific case that works for most of the easy to understand models, but not for this one. So let me just go back one step. If I do a post selection on one for the target qubit, I would expect that the resulting model just looks like these, right? So it just has these and it has these. So that's just the resulting model, right? So it's basically 1, 1, 1, right? Actually, these hyperedges are then by definition redundant, and so they just go away, and then it's just um, an unentangled state, right? They're all deterministically one. So if this is a post select for one as a measurement, and if I post select for zero, God, I never have time to get things fixed in terms of, performance is still crappy, everything is crappy, but anyway, I keep just pushing. If I post select on zero, then what is the resulting hypergraph, right? The resulting hypergraph, if I post select on zero, right, is that, well, that's a good question, because then I know that it can't be 1, 1. But how do I represent that without doing some funky transformations in here? I don't want to have to transform and change and create hyperedges when I do post selection. Post selection should just kind of say, what do I keep? What do I leave? What do I keep? What do I kick out? Right? And so I definitely keep the zero and I kick out the one. Right? So in an intermediate step would be 0, 0, 0. I kick out the 1, and so that hyperedge here becomes irrelevant. And then we have kind of this left, right? So this is the This is sort of the intermediate step. Now, how do I what do I do here, right? So what do I do here? Because I know that it's it's still entangled, right? Let me just double check. I think it's still entangled, right? Let me see if I can open anything like the browser window without the laptop crashing. Maybe once in a while, it would be cool. I wanted to open Quirk and check that quickly. So let's do incognito. And so Quirk. The starting point is a plus 0, and then I do a Toffoli gate, right? So I have these. And now I do a post selection for 0, right? And now I want to take a look at, yeah, I mean, that's kind of, it's still entangled, right? That's the state that I have. 33% chances for each of these states, but not this one. So that's still entangled. Yeah, that's what it is. This goes away. Now, there's an obvious way to represent that, which is that I would kind of now, for some reason, create more nodes, but I don't want to do that, right? A few spots on research, and you change the research for the study, right? You keep coming back and wishing me to have fun with the sessions. Thank you. Happy to have you there every day. Um, so how would I because if I remove the hyper edge, then essentially I'm that's not the correct model, because I can still have both independently. Oh, that's tricky, right? Because I don't want to, I could do something where I just say, well, we just kind of draw something like these instead, right? And get rid of these. In a way, it's like you're doing a complement, like sort of maybe a complement or something like that. Like, I don't know what the right term for these would be. Um, hmm. And this is where I'm stuck. Unless I would introduce some notion in the model where, why not? I mean, I could introduce a notion in the model where I have hyperedges that that mean the opposite, right? Or 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 I would just use the hyperedge. Interesting. Yeah, I could also assign like hyper edges, right? I'm not there yet, right? Where I play with the weights and whatnot of hyper edges, where I kind of say, hey, this specific combination has a um, mm, 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 has a specific probability and whatnot. But I could also just, which will eventually happen, right? Because it's the way that I'm going to deal with phase kickbacks and whatnot, and it can be that sort of hyper edges get a the hyper edge itself gets a relative phase, or gets a, right, because it's this is exactly what the situation where you're trying to express that it does not really matter where that like phase really is. It's not in any specific element, but it's in the combination of those. What I could do is I could use that to kind of say, well, I assign it a coefficient of 0, right? And that could be something uh, that could be something that I do in general. So I assign coefficients of zero to specific nodes. You know, I don't just delete things, right? But I assign if I pos select on 0. Why not? Because essentially that might even match with the idea that if I have also like a 0+1 state, right? Like somewhere in there, I basically have to just kind of keep a part of it, and I would keep it with the weight involved, right? Which is like in this case, like would be like the half, right? Um, so I could also just say what the post selection actually does algorithmically is say, okay, so I'm going to assign a probability. No, I'm going to assign the weight here to be 0. It changes the weights. I'm going to assign the weight here to be 0. And I'm not going to touch these ones, right? So therefore, then I have a hypergraph that I can use to still answer questions. And I'm modeling the fact that I'm actually accurately modeling the fact that these won't ever happen. I don't know exactly how, because then the other thing that I have to implement, right, is the, kind of get me the probabilities, right? Because there is still a chance. There is still a chance that if I go and take a look at the chance display, there's still a chance for these to be like on, right? It's just that the join probability is not there. So maybe that is the way to do that. Yeah, maybe that's the way to do that, to actually assign the probabilities. And that's maybe how I just, yeah, so the nodes have a weight to it. Um, and I think I should probably keep track of things, of things like, I should keep track of two things. I should keep track of the amplitude and the relative phase instead of just having the complex number. I think that's going to make it easier. Because I think those are the correct terms, right? Qubit amplitude and phase. I think these are the two things that then you can either combine. So you can either keep track of these things separately. Phase. So it is a two-dimensional vector space. That means that qubit takes two complex numbers. So a qubit takes two complex numbers to fully describe it. So this, right? Complex numbers. It's not detectable. So that is the, yeah, exactly. P. But in this case, So okay, so I can actually use that. I can just use the um, I can just use the phase, right, and the probability, because then I can compute it like that. That is a valid representation of a qubit. So um, yes and no, because I think no, I think I don't want to do it like that, because that is sort of the standard, but I just want to make sure that I can keep kind of global phases as well. So not to kind of compute always the relative phase one, um, but basically turn what you would use as alpha and beta, so the complex numbers, into the magnitude and sort of the polar form, right? I think that's the way it's called, polar form. So you have, yeah, I think the polar form is the way to go. And I think I should keep things like that. Well, I keep r and theta, right? Instead of x and y. The length of the vector and the angle. Yeah. Because I think the complex form, yeah, that makes operations in complex numbers easier. Uh, the modulus and the argument. Can probably use these names here. Does it though? I think it does. I think what it does is the multiplication becomes easier. So complex numbers, polar form, addition, operations in polar form. There you go. That's what I wanted to go. So I should make it easier. Addition. Oh, okay. So okay, cool. In polar form. So that's then the polar form is like that, right? So the addition and the modulus is the argument. Addition, subtraction. Okay, so from yeah, addition and subtraction is easier to have the rectangular form, exactly. But multiplication is easier in polar form. Yeah. Yeah, multiply by the two moduli and add subtract the arguments, exactly. Um, mm, 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 mm. Yep. Mm-hmm. I don't know what that does it make it. Would this make it easy or not? Do I need to add things or multiply things? I think I rather need to multiply things. I only need to add things whenever I kind of like, you know, talk about the same qubit, but when it will then come down to the specific probabilities of certain system measurements and stuff like that, I think multiplication will be the king. I don't know, but I think so, right? So I'll basically have so I can keep splitting things, blah blah blah. So each will keep the each kind of keeps the angle and keeps um, the amplitude. Hmm. Okay. I'm trying to think what will be what will be the best representation, but that's probably not a big. That's something I can figure out later. In terms of what's the question that I want to be able to answer most often. Um, I guess, yeah. I mean, I guess I can just go with the standard rectangular form, and this is just a zero, right? In this case, yeah. And so I'd go and each of so the nodes basically can have the nodes can have then that coefficient. We'll just call it coefficient, I think, and it's just going to be a complex number, one complex number. Like if a node, yeah, if the node is in the 0 + 1 state, um, that's still gonna have one coefficient, right? It's just for the plus state, I'd say. Uh, 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 yeah, and then that coefficient, needs to be multiplied, right? Whenever we'll be doing the splitting, that's an important thing as well. Yep. So I think I'll do that. I think I'll do that. But then what it means? So it means I will not get smaller. It means I will not get smaller hypergraphs. That kind of sucks. I'm not super happy with these though. That kind of sucks. I'm not really happy with not getting smaller hypergraphs though. It's just visually not like. I can then from a visual perspective just hide it, right? Just hide the nodes that like have the coefficient set to 0, but I can't hide the hyperedges. I can maybe mark the hyperedges from a color perspective too. I mean, it's not that. The truth is, maybe I can. It's like I don't know if I want to be consistent and just keep things like these with zeros, or I'd say no. Look, the nodes I'm going to delete, but the hyperedges, um, they're going to suck the 0 because the nodes are still there. They're just not there at that level, right? So I need to keep the hyper edge. Something to think about, but that's a good idea. Not a bad idea. I'll leave it here for today. Bye bye.